What if I told you that the world's most popular infrastructure platform already solved the same system design challenges that appear in every senior engineer interview? Kubernetes runs millions of containers across thousands of nodes, with automatic scaling, self-healing, and zero downtime deployments. But here is the real insight. The design patterns Kubernetes uses are not unique to containers. They are universal system design patterns. In this video, we will reverse engineer Kubernetes architecture and extract the system design lessons hidden inside scalability, reliability, durability, and resilience. Let us start with the big picture. Think of Kubernetes as a self-managing city. Every city has a city hall. That is the control plane. And it has neighborhoods with buildings. That is the data plane. In the control plane, the API server is the front desk. Every request goes through it. ECT is the records office, the single source of truth. The scheduler is the urban planner. It decides which building gets the next tenant. And the controller manager is like department heads. Each watches their domain and acts when reality drifts from the plan. On the data plane, each node is a building. The kubelet is the building superintendent. The container runtime is the construction crew. And kubeproxy is the mail carrier, routing traffic to the right apartment. This separation is the first design lesson. Decouple the brain from the body. The control plane decides. The data plane executes. Now, here is the most fundamental pattern in Kubernetes. Declarative design. You do not tell Kubernetes how to deploy step by step. You tell it what the final state should look like. Imagine a thermostat. You set the temperature to 72 degrees. You do not say, turn on the heater for 10 minutes, then check. No, you declare the desired temperature, and the thermostat continuously adjusts. Kubernetes works the same way. You write a YAML file, 3 replicas of my web server, 256 megabytes of memory each. Kubernetes reads the desired state, compares it to actual state, and acts to close the gap. This is the reconciliation loop. Watch diff act over and over. And here is the critical design choice. Kubernetes uses level-triggered design, not edge-triggered. It does not just react when something changes. It continuously rechecks full state. So if the system misses an event, a network hiccup, a crash controller, the next loop catches the drift and fixes it. This makes the system self-correcting. In system design, this is convergence. The system always moves toward desired state, no matter what happens. Scalability. How does Kubernetes handle growth from 10 pods to 10,000? The API server is stateless. It stores nothing locally. You can run 3, 5, or 7 instances behind a load balancer. Any instance handles any request. Horizontal scaling at its finest. But every request touches ECT, the records office. ECT uses Raft consensus, where writes go through a single leader. So how does Kubernetes prevent ECT from becoming the bottleneck? First, the watch mechanism. Instead of polling, clients open a long-lived watch stream. ECT pushes changes in real time. This is publish-subscribe, reducing read load by orders of magnitude. Second, the informer pattern. Each controller maintains a local in-memory cache. It syncs on startup with a full list from the API server, then stays updated via the watch stream. The controller almost never queries ECT directly. This is local caching with change data capture, a pattern found in databases and event-driven systems everywhere. 4 pod-level scaling. The horizontal pod autoscaler watches metrics, CPU, memory, custom metrics, and adjusts replicas automatically. For node-level scaling, the cluster autoscaler detects pods stuck in pending and provisions new machines from the cloud provider. The lesson: scale each layer independently. Stateless components scale horizontally. Stateful components use consensus and caching. Reliability. How does Kubernetes keep services running when things fail? It starts with ReplicaSets. A replica set is a guarantee. I want 3 replicas of this pod, and the controller fights to maintain that number. If a pod crashes, the controller sees desired 3, actual 2, and creates a new pod. Think of it like a franchise. Always keep 3 restaurants open. If one closes, open another immediately. But how does Kubernetes know if a pod is healthy? Health probes. 3 types. Liveness. Is this container alive? If not, restart it. Readiness. Is it ready to serve traffic? If not, remove it from endpoints. Startup. Give slow starting containers time before liveness checks begin. This is the circuit breaker pattern. Instead of sending traffic to a broken instance, Kubernetes removes it from rotation silently. For planned disruptions like node upgrades, PodDisruptionBudgets set a floor. At least 2 of 3 replicas must stay available. Even during a rolling upgrade, Kubernetes never takes down more pods than the budget allows. The lesson: reliability is not about preventing failures. It is about detecting fast, isolating, and recovering automatically. Durability. How does Kubernetes protect state across crashes and hardware failures? The most critical component is ECT, which uses the Raft consensus protocol. Imagine a city council with 5 members. To pass a law, you need a majority, at least 3 out of 5. In Raft, the leader receives all rights. Before applying a right, the leader sends it to followers. Once a quorum acknowledges, the right is committed. If the leader crashes, the remaining nodes elect a new one. No single point of failure. But what if the leader crashes mid-write? That is where the write-ahead log comes in. Before applying any change, ECT writes it to a sequential log on disk. If ECT crashes and restarts, it replays the WEL to recover exact state. Think of a ship's log. Every event recorded before it happens. For application durability, persistent volumes provide storage that outlives any pod. And stateful sets give each pod a stable identity and dedicated storage across restarts. The pattern: separate compute from storage. Compute is ephemeral. Storage is durable. Use consensus plus write-ahead logging. Resilience, the ability to absorb failures and keep operating. Kubernetes expects failure at every layer. Start with self-healing. If a container crashes, the kubelet restarts it with exponential backoff. First restart after 10 seconds, then 20, then 40, up to 5 minutes. This prevents crash loops from overwhelming the system. At the node level, if a node stops sending heartbeats, the controller marks it not ready after 40 seconds. After 5 minutes, pods are evicted and rescheduled on healthy nodes. Automatic disaster recovery, no human needed. The control plane runs as a multi-master setup. 3 or 5 ECT nodes for consensus. Multiple API servers behind a load balancer. The controller manager and scheduler use leader election. Only one active, but standbys ready to take over in seconds. For workload priority, Kubernetes supports preemption. When a high-priority pod cannot be scheduled, the scheduler evicts lower-priority pods to make room. Like an emergency vehicle, it gets priority, regular traffic yields. The resilience lesson, designed for failure at every layer. Build automatic detection, isolation, and recovery into the architecture. Let us extract the system design patterns we have seen. Pattern 1. Reconciliation loops. Instead of reacting to individual events, continuously compare desired to actual state. This is idempotent and self-correcting. Use this in any system where state can drift. Pattern 2. Level triggered over edge triggered. Do not rely on catching every event. Periodically recheck full state. This makes the system robust to missed notifications. Pattern 3. Watch with local cache. The informer pattern. Full list on startup, then incremental updates via a watch stream. This reduces load on the central store while keeping clients up to date. Pattern 4. Optimistic concurrency control. Instead of locking resources, use version numbers. Kubernetes uses resource version. If the version has changed since you read it, your update is rejected and you retry. No locks, no deadlocks, and high throughput. Pattern 5. Admission control pipeline. Before any write is persisted, it passes through a chain of mutating and validating webhooks. This is the middleware pattern for data integrity. Pattern 6. Leader election via leases. Lightweight leadership without external coordination services. The leader renews a lease periodically. If it fails, another instance acquires the lease. Every one of these patterns appears in databases, message queues, service meshes, and cloud infrastructure. Kubernetes is a working textbook of distributed systems. For architects and senior engineers, here is how to apply these patterns in your own systems. Use declarative APIs. Let clients declare desired state and build controllers that reconcile. This makes your system self-healing by default. Design your control plane to be stateless wherever possible. Push state into a dedicated, consensus-backed store. This lets you scale horizontally without coordination headaches. Implement health checks at every boundary. Liveness probes for internal health. Readiness probes for external traffic. Startup probes for initialization. 3 distinct signals for 3 distinct decisions. Use optimistic concurrency instead of distributed locks. Version your resources. Reject stale writes. Let clients retry. And finally, make every operation idempotent. If a controller crashes mid-reconciliation, the next iteration should produce the same result. Idempotency is the foundation of self-healing systems. Kubernetes did not invent these patterns, but it implemented them at a scale that proves they work. Let us bring it all together. Kubernetes teaches us 6 system design principles. First, declare the what, not the how. Declarative over imperative. Second, reconcile continuously. Watch diff act. Level triggered, not edge triggered. Third, separate brain from body. Stateless control plane, durable state store. Fourth, scale each layer independently. Cache aggressively. Watch instead of poll. Fifth, build for failure. Health probes, automatic restarts, leader election, and preemption. And sixth, protect state with consensus and write-ahead logging. These patterns are not just for container orchestration. They are the building blocks of every reliable distributed system. Learn them from Kubernetes. Apply them everywhere. Thank you for watching.